Yesterday, we had just finished up talking about finding enthalpy change, calculating enthalpy changes. We talked about the enthalpy of combustion experiment, how we can burn a fuel and measure the temperature change of the water in order to calculate our enthalpy. And when we do that, we are calculating the heat transfer of the water to the Q for the water. That's going to be negative Q of the fuel. And then you're also going to, because we have per mole, going to need to know how much fuel did you burn to get that calculation, right? So I asked you guys to go back to the problem E on page 10 and take a look at that. Before we do that, I can't remember if we went through this question, but I don't think we did. This is a question bank question about, or it's similar to a question bank question about this kind of experiment. Okay, so this is saying, okay, we've got this setup here. Ethanol is being burned. We've got a copper calorimeter with a draft shield around it. We've got an insulator on the top, and we've got a thermometer measuring the temperature of the water. And the question here is, it's essentially an evaluate the experiment question. So it says, which would lead to an experimental result which is less exothermic than the literature value? So less energy coming out of the burning of the fuel, of the combustion reaction, okay? So what would understate the amount of energy in the fuel? So one option is heat loss from the sides of the copper calorimeter. One is evaporation of the alcohol. That's number 2. And number 3 is the thermometer touching the bottom of the calorimeter, if the thermometer was touching the bottom. And we want to know which things would lead to something that underestimates how much energy is coming out of burning the fuel. Okay? So think about that for a minute. So we've got heat loss from the copper calorimeter, evaporation of alcohol, and the thermometer touching the bottom. Let's just look at these individually. Losing heat from the calorimeter, is that going to overestimate our energy or underestimate our energy released? Underestimate. Why? So, sorry, I'll just say it because you haven't thought about it as long as I have, for sure. But if we're losing heat, that heat is not going into the water. If we're losing heat from the calorimeter, that is heat being lost essentially from the water. And that is temperature that is not changing, right? That is something that we are not recording with our thermometer, because all we're recording with our thermometer is the change in temperature of the water. So if we're losing heat from the sides of the calorimeter, that heat is not being accounted for in our measurement of temperature, okay? How about evaporation of alcohol? If the alcohol is evaporating, what's that going to do? Hinta? Yeah, it absolutely is part of our equations, but like you said, not the heat equation, right? The heat equation is all about the water. However, we're going to take that heat transfer and we're going to put it over moles burned, okay? So if I am losing alcohol that is not being burned, I'm going to end up with what I think is more moles of alcohol contributing to that heat than actually was contributing. Because if it's just evaporating and not burning, then it's not going into that the heating of the water. So that's going to be, if we think about that our enthalpy is in kilojoules per mole, right? If I am overestimating the number of moles that are being burned, then the enthalpy is going to be smaller, right? So if the alcohol is evaporating without burning, then I'm going to think that this number is bigger than it is. And that's going to make the overall delta H smaller. Okay. How about the thermometer touching the bottom? Yeah.
That's because the heat is like directly on the thing, it's actually going to overestimate more.
Yep.
Not less.
Exactly. Exactly. So these are both going to bring it down, the enthalpy estimate down. This is going to bring it up. And so the answer would be 1 and 2 only for this. Okay. Okay. How many of you did this problem? Anybody? Okay. Let's talk through it first, and I'm going to give you a minute to do the calculations. Okay. So this is on page 10. Problem E. Same thing, combustion of ethanol. Enthalpy of combustion of ethanol, heating up a copper calorimeter, contains 100.0 centimeters cubed of water. And using a spirit lamp, it's heating that by burning the ethanol. And these are the data that were collected. So we've got initial and final temperature of the water, and we have mass of ethanol burned. Okay? And we want to know what is delta H in kilojoules per mole. What is the first equation that we're going to use here? Or what is the main equation that we're going to use here? That we were talking about yesterday. Yeah. Mm-hmm. Okay. Let me actually take a look because I can't remember now. Yes. So in your data booklet, so if this is the exam and you have this as a question on paper 2 or paper 3, because it could be either one, given this is experimental, it could also go in paper 3, you will have access to your data booklet. In the data booklet, section 1 is a bunch of equations. So if there's ever an equation that you're like, oh, I can't remember what that one is, look and see if it's in section 1. And here you will find it organized by topic number. Okay, so we're in topic number 5, and here we are, 5.1, Q equals MC delta T. Okay, so you don't have to memorize it, it's in here. It's a good idea to memorize it anyway. If there are things that you're looking for that are constants, you can also look in section 2, physical constants and unit conversions. However, I believe, oh no, here it is. Specific heat capacity of water, 4.18 kilojoules per kilogram per Kelvin or joules per gram per Kelvin. Okay, so specific heat of water, it's easiest if you memorize it, but it's here if you need it, okay? So don't forget that you have that data booklet. All right, we've got initial and final temperature. We've got our C, right? What's our M? Yes. Why is it 100 and not 1.78? Exactly. Because this is the heat gained by the water. We've measured the delta T of the water. We're using the specific heat of water to calculate it. So we need the mass of the water. How do we know it's 100? Because we were given the volume, 100 centimeters cubed, same thing as 100 milliliters. And we know, this is something you absolutely should have memorized, that the density of water is 1 gram per milliliter. Okay? So this is equal to 100 grams. Technically 100.0 grams. Okay? So we can plug all that stuff in and calculate our Q. So go ahead and do that. Thanks. Yeah. Say. Sorry. Second. What? Oh. Yeah. Hang on. Let me move some stuff over. No problem. All right, so what is Q? Who's got a number for me? What about units? Units for heat. Nope. So if you look in your data booklet, you will see that the specific heat of water is given you as 4.18. One of the options is joules. Sorry, I should write it the way they do it. Joules, capital J, that's our unit for energy. Gram to the -1. And is it K or Celsius? Yep, K. Did anybody convert their temperatures to Kelvin instead of degrees Celsius? Did you have to? You did not have to, okay? Because it's the same scale, just shifted. So 1 degree, a change of 1 degree Celsius is the same as a change in 1 Kelvin, and since all we care about is the change in temperature, we can say this is the same thing as degrees Celsius, okay? So this is going to be now times grams, right? Because that's our mass, times, we'll just call it Kelvin, okay? When we do this. So our grams is going to cancel out. Grams to the -1 and grams. Temperature cancels out. Temperature on the bottom, temperature on top. We end up with joules. Okay, so heat, energy is always in joules. Now, we could say joules here. We could also convert this, if you wanted to kilojoules. You could say 14.630 kilojoules. Okay, both mean exactly the same thing. Don't have to do one or the other. Except that the question does specifically ask us to do it in kilojoules per mole, so make sure that you are paying attention to the units that the question is asking for, because they will mess with you that way, okay? So we want, this is how much heat was absorbed by the water. Is that the answer to our question? It is not, okay? This is how much heat was absorbed by the water. We want to know the enthalpy, the delta H of combustion of the ethanol, okay? So, first of all, the energy that was gained by the water, we're going to set as equal to the energy lost by the ethanol in the combustion reaction, okay? So we're going to say that, so this is Q of the water, Q of the reaction is negative 14.63 kilojoules, okay? Because it's just losing is negative. It's an exothermic reaction, releasing energy. You're going to have a negative Q. So now is this our answer? No, why not? What is the question asking for? What units are we looking for? Kilojoules per mole. We don't have any moles in here. So we got to get the moles in here somewhere. That's why you have grams of ethanol. Okay? That's why that data is in there, because you need to use that to get the moles. Okay? So you're going to take your 1.78 grams of ethanol and you're going to multiply it. You're going to do a little dimensional analysis. We're putting grams on the bottom, moles on the top, because we want moles. And what are we going to use to do that conversion, to convert from grams to moles? How do we go from grams to moles of a substance? Yeah. Say what? We do put 1 at the top. Yes, absolutely. What do we put at the bottom? Or where are we going to get the number to put at the bottom? From the periodic table and from the formula. Okay? So, carbon, 0.01 times 2, hydrogen, 1.01 times 5, or times 6, sorry, because there's 2 of them. Don't forget to put the hydrogens together when you're calculating molar mass of the carbons and the hydrogens if it's given to you in the condensed structural formula, or the for organic compounds, how we put the functional group there. So make sure you don't forget about that last hydrogen. And then oxygen, 16 times 1. Do those calculations, and then we add them up and get a total. So it's going to be 24, 6.06, 16. So that's going to be 46.06. That is our molar mass. That is what we are using, the molar mass of the substance. The units for that are grams per mole. And that's always 1 mole, like Brown said. So when you're using the molar mass, moles are always 1. And so we're going to stick that 46.06, assuming I did the math right, which I don't promise, on the bottom here. And this is essentially over 1 or over nothing, right? And we're going to multiply across the top, divide by the bottom. The top is just 1, so you might as well just take 1.78 divided by 49.06. And we only have 3 significant digits here, so we only get 3 significant digits in our answer, and that is how many moles we have. Now what do we do? So now we have kilojoules, and we have moles. And we want our answer to be in kilojoules per mole. So what do we do with those two numbers? Divide them. 14.63 divided by 0.0363 equals whatever that number is. So I have, this is going to be negative because remember our heat was negative. 403 kilojoules per mole. Or I'll write it the way they do. Moles to the negative 1. And that is our change in enthalpy. A lot going on here. Okay. And this would probably be only one part of a paper 2 or paper 3 question. They might ask you to draw the Lewis structure of ethanol. Or they might then say something about if you had ethanol and you did an oxidation reaction and you wanted an aldehyde, what conditions would you do that reaction in, right? And then they might ask something else about why is the boiling point of ethanol as high as it is? And they might, there's a lot of things they could ask here, and that's typically how the paper 2 and paper 3 questions go. They're going to jump around between topics, and this might just be part of it. But yeah, so things to keep an eye on. What are you measuring the temperature of, the temperature change of? Most of the time, it's going to be water. So make sure you are also paying attention to the mass in terms of the water or whatever it is that you're measuring the heat change of. Not always. They might talk about changing heat in a cylinder, a metal cylinder or something like that, where they're going to ask you to calculate specific heat. Could be a variety of things. Okay. So that is all we're going to have time to talk about in terms of the first half of topic 5. There's lots more practice problems in the packet that I gave you, which I know I haven't posted the answer key to that yet, but I will. The answer key to the study guide is already posted, so you can do extra practice problems that are in the study guide that we haven't gone over in class and check your answers. Those are all options, and I will make sure I get the answer keys to the practice questions, the question bank questions up today. All right, the second part of the energetics is talking about this thing called Hess's law. Second part of this topic. And Hess's law and enthalpy cycles. Because sometimes you can't measure the enthalpy change of a reaction. There might be some reason, maybe it's just not possible to do the reaction under conditions that you have available to you, there might be, for whatever reason, you cannot actually measure directly or find directly the enthalpy, change in enthalpy of a reaction. But you still want to know it. Well, it turns out you can take a longer path. you can take a winding road to get there, and it will give you the same answer in the end. And that's what the rest of this topic is about. So if you imagine yourself climbing this mountain, it would be nice if you could take the direct straight path right up the mountain, but there's no path there, and there's probably a lot of bouldering. It's probably very, very, very steep. It'd be very difficult to do. You don't really want to do that. However, there's this nice switchback path. The change in location from the beginning to the end is the same, no matter whether you take as the crow flies or walk on the trail. Okay, you are still traveling net the same amount, right? Getting to the same place, getting to the same answer in that sense. And we can do the same thing with reactions. So, clear this. Hess's law says that the enthalpy change is independent of the route by which the reaction occurs. So if, say, we know the change in enthalpy going from A to B, and we know the change in enthalpy going from B to C, but we do not know what it would be going directly from A to C. We can use what we know to calculate what we don't know. And so basically we can say, all right, instead of going directly, I'm going to take this route and then this route. But if I add those together, if I take the sum of the steps that I've taken, it's going to add up to the same thing as if I had taken the same straight path. Okay, so this allows us to find a lot more information about energy and reactions than we might be able to do experimentally. Okay. So that change is the same as the sum of these changes. Okay. Now, let's give it, just as an example, here's change in enthalpy. We want to find what happens when we take carbon, hydrogen, and oxygen and turn it into CO2 and H2O. Well, we don't have that number. We don't know. We can't do that in a reaction system in our lab. But we do know what happens when we put carbon and hydrogen together to make propane. We do know the enthalpy of that reaction. And we know the enthalpy of the reaction where we burn that propane with lots of oxygen to make carbon dioxide and water, which is the products that we eventually want to end up with. So we're going to take the sum of this enthalpy and this enthalpy will be equal to this. So we're just adding them up. Okay. Now the key here, we can add them just as they are, negative 105 plus negative 2219, because we are traveling in the same direction that the arrows are going. Okay? If I wanted to travel in the opposite direction, then I would need to take the opposite sign. Same number, enthalpy of the reaction is still the same, but the sign is opposite. Just like heat added is the same as heat added to one thing is the same as heat released by the other thing, assuming we capture all of that. Same idea here. The energy that goes into converting our reactants to our products would be the same thing as the negative of the energy that goes into taking our products and converting them back to the reactants. Okay. Let's not do that right now. There's two main ways that we use this idea of these enthalpy cycles. Well, there's actually three, but there's two for which drawing that triangle is actually really helpful. One is by looking at standard enthalpies of formation. So what this is the, I think I have it actually on here. Yeah, so this is page 13 on your study guide. Standard enthalpy of formation is the change when 1 mole of a substance is formed from all of its elements in their standard states under standard conditions. So it's going to have that little plimsoll thing on the top. Okay, the delta HF with a little theta looking thing. Okay. And so we're basically trying to make something out of its component parts. And a couple of things are important about this, though. One is that if the element is already in its standard state in the reaction, then that enthalpy change is 0. The enthalpy of formation of that is 0 because it's already there. That applies to something like an element by itself like iron. That's just like maybe that's one of the reactants or one of the products. Enthalpy of formation of iron is 0 because it's already in the most basic state it could be in. It's also true for our diatomic elements. Things like oxygen. In their standard state, they exist as O2, N2, H2, etc. And so if you have O2 in your reaction, the enthalpy of formation of that is 0 because it's already in its standard state. And if you don't remember which ones are your diatomic elements, this is the mnemonic that we like to use, which of course is completely false. However, I have no bright or clever friends. Iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, fluorine. So if you can remember, I have no bright or clever friends, you've got your diatomics. You can also, if you're more of a visual person, you can remember that there are 7 of them. And 6 of them make the number 7 on the periodic table over in the corner there. And then there's you got to add hydrogen. Okay? So these are our diatomic elements. Enthalpy of formation of any of these in its diatomic state is 0. All right, so back to page 13. Say we want to find the enthalpy of formation of methane, CH4. Well, what are the parts of methane? It's carbon and hydrogen. Okay? So one of the things that makes up the methane is carbon, which in its standard state is a solid, like the graphite in your pencil. The other one is hydrogen, but that's going to exist as H2, so you're always going to write it as H2, and that's going to be a gas. And we want to balance this equation, so we're going to put a 2 in front of the H2 so that we get a total of 4 hydrogens on both sides, 1 carbon on both sides. And we can get a delta H formation for methane. Now, sometimes you're going to get something weird that you were told in honors chemistry we never ever do. But here it is. We do it. We lied. You're going to get fractions. The reason you're going to get fractions is because enthalpies of formation are always in terms of 1 mole of product. Whatever substance that you're forming, it's 1 mole of that substance because it's still kilojoules per mole. So it's from the perspective of the substance you're forming. Which means if I have coefficients for this equation that are 4C, 6H2, 1O2, and 2 ethanols, I'm going to divide all those by 2 to make sure that my ethanol is only 1 mole. And that's going to give me half of an O2 molecule. And you do not write this as O by itself. Half of O2, half a mole of O2 is not 1 mole of O by itself, because there is no such thing as O by itself in a standard state. So it is going to be 1/2. Okay, so you are going to see that in some of these reactions. Okay. How do we then use these? You've got a whole table of these in your data booklet. You've got somewhere in the tens, somewhere. Table 12, selected compounds, thermodynamic data, delta HF in kilojoules per mole is one of the columns there. And so we will talk on Monday about how we use that to calculate enthalpies of reactions.